But again, today we're going to try to get as much of the notes done in class as possible. Tomorrow, whatever we don't get done, we can finish up. But plan on having, if not the whole class, most of the class tomorrow to do homework to make that a full work day. Just so you guys know, again, I don't know if you, I know I had said it the other day, but if you saw it on the homepage, we will have a take-home quiz given in class on Thursday, and I'll give you the long weekend to do it, and then that'll be due in class on Tuesday, not like midnight on Tuesday. That's going to be due in class on Tuesday. Like I will collect that from you on Tuesday, grade it, and then we'll do section 1.5, and then we'll have our chapter 1 test later on next week, I think. But just so you know, that's coming on Thursday. You'll get it on Thursday. I'm going to give you the entire period to work on it on Thursday. And so you can work together if you'd like. But the only thing is you just can't use me as a resource. You can't ask me questions. You can ask each other questions. You can help each other along if you'd like to. That's totally fine with me. Take it home, think things through, and then when you come back on Tuesday, it's due in class on Tuesday so I can start to grade it. There we go. So section 1.4, exponential functions. So we're going to spend two sections, section 1.4 and 1.5. Section 1.4 is going to be on exponential functions, and section 1.5 is going to be on logarithmic functions. Okay, 1.4 is going to be exponential, and 1.5 is going to be logarithmic. So kind of taking a little bit more in-depth look at exponentials and logarithmics. So the function 2 to the x is called an exponential function because the variable x is the exponent. Whenever you put a variable up in the exponent, it behaves as an exponential pattern, increasing exponentially. It should not be confused with the power function x squared, where the x is as the base and the number is the power, right? In general, the exponential function is f of x is equal to b to the x, where b is a positive constant. Now, remember what that means. That just means it's repeated multiplication, right? Repeated multiplication n amounts of times. So if x is equal to a positive integer, then b to the n is equal to b times b n times over. If x is equal to 0, then obviously b to the 0 is equal to 1. Okay, and this is assuming that b is non-zero, right? 0 to the 0 power. Actually, I used to show a video on this for one students. 0 to the 0 power is actually one of those things that's undefined. Some people say it's 0, some people say it's 1. Mathematicians have differing opinions on that. But we're assuming that this is non-zero there because if the base was 0, things would be weird anyway. But if b to 0 is equal to 1 and if x is equal to negative n, where n is a positive integer, then b to the negative n is equal to 1 over b to the n. So remember that if you have a negative exponent, that just flips it into the denominator, right? Negative exponents flip it into the denominator. So that would be like 1 over 2 to the second power, 1 over 2 to the third power, 1 over 2 to the fourth power. It would just be making it smaller and smaller and smaller. The bigger values of x would actually make the number smaller when you have a negative exponent. And that's something that's going to be very, very important. If x is a rational number like p over q, where it's a fraction, remember that is, it might be a good idea to write down that rule where if b to the p over q is equal to the qth root of b to the pth power, whatever you want to say that. So q is the index, p is the power, right? Where you have that the denominator of the fraction is the root, and the p is the power. Okay. Now that is commutative. I can change the order there. I can take the root first, then the power, or the power first, then the root. So it doesn't matter how you take them; just take one before the other. And that might lend itself to helping you in a certain way solve something. Where if you take the root first or the power first, it might simplify down something a little bit easier. All right, let me show you some graphs of exponentials here in a minute. You'll see some people writing, but let me show you some graphs of some exponentials, just to show you what some of these are going to look like. Because there's standard things about the graph of an exponential. There are standard things. There are standard, things that may happen. Well, let me just show you. Just stop talking to show you. The graphs of members of the family of functions y is equal to b to the x are shown down there for various values of my base. Notice that I am changing the base. Can I make this a little bit smaller so we can all see it on one page? There we go. That's a little bit better. So all I'm doing here is changing the base of the function. Changing the base of the function. If I just kind of like take our standard 2 to the x, like I don't know why, it just seems like 2 to the x is almost like our parent. It's not 1 to the x because watch what happens when I flip it to 1. 1 to the x just flatlines, right? 1 to the third power is still 1. 1 to the eighth power is still 1. 1 to the negative second power is still 1. So no matter how high or low my power gets, 1 to the x is just a flat line. But for some reason, we always think of 2 to the x for some reason being almost like our parents, one of the most basic exponentials that we could get. Okay, so we have 2 to the x. If I start making that exponent, that base, I got to be careful there. If I start making my base bigger and bigger and bigger, it will make that exponential steeper and steeper and steeper. Like if you compare 2 to the x to 10 to the x, 10 to the x is going to go up at a higher rate, right? Obviously, if I take 2 to the something power, 10 to the something power is going to go even greater rate, right? So the higher you make your base, the steeper your exponential gets. The lower you make your base, so the closer and closer I get to 1, the more it starts to level out. So the closer and closer it gets to that flat line. And then as soon as you put it below 1, look what happens. I've got 1/2 to the x. Now instead of an exponential growth, I see an exponential decay. And the smaller and smaller I make that base, the steeper it gets in terms of its decay. Okay. Now, some things that are always standard, there's still that asymptote on our x-axis. I haven't shifted it away. I don't see any plus or minuses on the outside, so it did not get shifted up or down at all. So the asymptote doesn't get shifted either. The asymptote is still on the x-axis here. Okay, no matter what I make my base, the asymptote is still on the x-axis. But things to take note of is the fact that if it's a number greater than 1, then it's going to be an exponential growth. If it's a number less than 1, that's going to be an exponential decay. And another key thing here is, this is no coincidence there. Right, look at all those intersecting right there. What is my y-intercept for all of these? 1. What's anything to the 0 power? 1. Right? The only exception being 0 to 0 power. Anything to the 0 power is 1. So the y-intercept is always going to be 1. Notice that all of these graphs pass through the same point, 0, 1, because b to the 0, no matter what b is, as long as it's non-zero. Oh, they do make that special point here. They do say for b is not 0. It's always going to be 1. Notice also that the base b gets larger, the exponential function grows more rapidly, like I talked about. You can see in the figure down below that there are basically 3 kinds of exponential functions. And I don't even know why we would consider this as an exponential. This seems like more of like a constant function, but whatever. Okay, I see the variable in the exponent is technically exponential. I see 3 types of exponentials. One that it is a decay, one that it is a growth, and obviously our flat line there, our constant exponential. Notice that the domain is always all real numbers. It doesn't matter what I plug into the exponential. I could take anything I wanted as an exponent. I could take a whole number. I could take a fraction as an exponent, like I said, with taking the root. I could take an irrational number as an exponent if I really wanted to, because again, it's just a number in that case. But the range is going to change depending if I move it up or down. The range is kind of a standard 0 to infinity. Notice that it does not equal 0. That's the idea of an asymptote, right? It's going to get closer and closer to 0, but never reach it. It's going to be 0 to infinity unless I shift it up or down, unless a vertical shift has happened. Okay. And notice, I think this is a good point to bring up here. If you put a reflection on b to the x, a reflection over the y-axis on b to the x, that's going to change b to the x into b to the negative x. And b to the negative x is just 1 over b to the x. So notice that the exponential decay and exponential growth are just reflections on one another over the y-axis, because it's just b to the negative x. Okay. As long as you have the same base. Just taking the standard b to the x. All right, some good friends of ours, the properties of exponents. We've definitely been learning these since, I don't know, probably 8th grade maybe? Well, that was algebra 1 for you guys. 8th grade. But I think even in like maybe it's seventh grade. Properties of Exponents. If not, definitely an opera. If a and b are positive numbers and x and y are any real numbers, then b to the x plus y is b to the x times b to the y. B to the x minus y is b to the x over b to the y. B to the x to the y is b to the xy. And then a times b to the x is a to the x, b to the x. Again, we've been learning these properties for a long, long time. Get nostalgic. This is like the last time you'll have to write down exponent properties. Oh, cool. Just think, like for some of you, this may be like the last math class you're ever forced to take. Like beyond this point, you're choosing to take math classes. Well, I guess you kind of chose to take this class too. But like in college, you choose to take those classes because you choose your major, you know. So this may be like the last math class you ever take. The beginning of the year. So again, just to kind of make note of a couple things here. If you are adding within an exponent, you are multiplying with bases, right? If you're adding within an exponent, you are multiplying with bases. If you are subtracting within an exponent, you are dividing with the bases. If you are taking a power to a power, you are multiplying with the exponents. And if you are taking the product, or excuse me, the power of a product, then you can basically just distribute that power. Now be careful here, okay? Let me just reinforce this. This is true where I can distribute this power. You know, that is kosher. You can do that. What you cannot do is distribute that power. Like this is a no-no, right? Don't do that. You can't do that. That's a very common mistake, but you can do this. Why? Because this is a plus and that's a product. Okay? You can't do it on a plus or minus sign, but you can do it on a product. Now to run students always flip that around. All right, sketch the graph of the function 3 minus 2 to the x and determine its domain and range. Sketch the graph of the function y is equal to 3 minus 2 to the x and determine its domain and range. So let's sketch. First thing I'd like to do is put the exponential first. I'm going to say negative 2 to the x plus 3. Negative 2 to the x plus 3. I'm going to graph that. Again, 2 to the x is kind of like our standard, you know, until we learn about e to the x. This is kind of like our standard. All right, so our parent, again, just a sketch, folks, just a sketch. A parent is going to look generally like this. That's 2 to the x, where this is at 1. Okay, what's going to happen to it first in terms of order? I see two things happening. Now, does the 2 have any sort of transformation happening? The fact that it's 2 just shows you what the graph is going to look like, right? If I change the base, obviously it's going to be a little bit steeper, but that's not truly a transformation. Okay, the base stays the base no matter what. But I see 2 transformations. I see a negative and a plus 3. Good. No, you're right. Reflected across the x-axis because I changed the y-value, right? And then the plus 3 makes it go up 3 units. So the reflection is going to happen first. Reflection is going to happen first. And it's a reflection across the y-axis. So that means this is going to be true, right? This is negative 2 to the x. And then I shift it 3 units up. Now this was down here at negative 1 now, right? So now I shift it 3 units up. Let me put it in green. Okay, so this is going to go to 0 to 1 to 2. Okay, so there's my y-intercept. And it's going to look... Now, can anybody tell me where... Oh, I should have made it steeper than my red one, but you get the idea. Can anybody tell me where is my asymptote now? Ooh, they're really hyped up over there playing Kahoot. They're really hyped up. Where is my asymptote? It's at 3. Yeah, it's at 3. Because thinking about my asymptote here, right? The asymptote was at 0, right? When I reflected it, did it change? No. Now I shift it up 3 units, and then since it's a horizontal line, shifting it up 3 units is also going to change my asymptote 3 units up as well. So I know my asymptote is at the line y equals 3. Why do I point that out? Because it's important to point it out for my range. Now my domain is going to be all real numbers, but my range, I only want points below 3. I only want points below 3. So from negative infinity to 3. Do not put a bracket around 3. It's never going to reach 3. All points below 3. Questions about that one? And again, we could use our graphing calculator to confirm, but we're good. All right, it says use a graphing device to compare the exponential function 2 to the x and the power function x squared. Which function grows more quickly when x is large? I mean, you could do this with me if you want, but honestly, I'm just going to graph these real quick. Go to my y equals. Beep, 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 beep. Come on. We got x squared. Let's make f of x 2 to the x. And then we got x squared. I'm going to zoom 6 this, put it to my standard 10 by 10. There's my exponential. There's my quadratic. Now, let's run that again. Watch as it goes through. Here's my exponential. There is my quadratic. Doesn't it look like my quadratic overtakes my exponential in terms of steepness? It looks like it overtakes it. Now, you guys can see it in color. I just have black and white here. Come on, make it a little bit bigger. But let me outline it for you. Here's my, I'm going to put F in blue. And then here's my, actually, I should have made that a little bit more shallow. Oh, please. Oh, really? Okay. And here's my quadratic. Okay. That's what we see. I'm kind of exaggerating the differences between the two, but it looks like the quadratic overtakes the exponential. Now, why is that the case here? But now, in terms of like what we know about an exponential, it's going to grow really fast, really quickly. In our brains, I mean, I think it would definitely be an exponential is going to grow faster. But why are we seeing it overtake it? Well, because we're stuck to our 10 by 10 window. Like if I did this, if I just changed my window, I made the x values the same, but then my y values, like I made it to like 100. Let's keep it at negative 10, but then go up to 100. Let's see what that makes it look like. I'm just kind of playing around with the window. There's my exponential. And there's my quadratic. Do you see how it crossed back through again? Right? Here's my exponential, and here's my quadratic. Look how shallow that looks now, right? What we were looking at was a window that big, okay? What we were looking at is a window that big. There's actually a full, I don't know if it's a lesson or just part of a lesson, where it's titled, "The Lies Your Calculator Tries to Tell You." It's like a section in the book. But again, what I'm looking at here, what I'm trying to tell you is that there are going to be times when your calculator is going to lead you to believe something different than what's actually happening. Always try to think logically about what's going on before, and not just trust your calculator all the time. Because here we might have looked at this normal 10 by 10 and said, "Oh, a quadratic grows steeper than an exponential." But we know different. Logically, we know that an exponential is going to go way faster than a quadratic will in the long run. We just weren't looking at it over the big picture. Okay. Is this bell ring at 9:17? Yeah. That's a good place to stop then. because now we're going to get into exponential growth.
I don't think he understands how stupid.